In this video, we're going to talk about ions. This is really going to be the first significant mention of ions for us in the course. That's perhaps a little bit different if you have friends who are in one of the other sections where some of the other faculty might be keeping a little bit more to the sequence of the textbook than I am. But this is a good time for us to talk about ions because it'll help broaden the number of reactions that we can look at and do stoichiometry calculations for, okay? So when we talk about ions, what an ion is it's a charged particle, okay? So it's an atom or a group of atoms that has an electric charge on it. And that means it's not got the same number of electrons as protons. Right? There's some sort of chemistry-specific vocabulary to these things. Ions with a positive charge are called cations. Ions with a negative charge are called anions, okay? There's nothing wildly important about remembering those words other than I will say them and you'll make sense of things a little bit faster if you get used to the idea that one of them is the positive and one of them is the negative ion. So the simplest ions we can talk about are what are called monatomic ions. Monatomic, just like the word looks like, if you think about word origins or roots or anything like that, that means one atom. Okay, so this is a single atom. Cation means positive charge. So this is going to be a single atom that has a positive charge on it. Right? The kinds of atoms that make these ions are generally going to be metals. If I want to picture how this happens, it says a neutral atom somehow loses an electron. Something causes an electron to be taken away from that atom. All right. The atom doesn't just spit out electrons on its own, right? If we leave it alone, it doesn't give off electrons. It requires some energy to pull the electron free from the atom. But in the case of a lot of metals, it doesn't require a lot of energy. And so this happens fairly regularly. The elements that you will see by far the most often in this course as monatomic cations are those over here in the first couple of columns of the period. Oops, hang on, I don't have the pen selected. That's why it didn't write. Over here in the first couple of columns of the periodic table, those things are going to consistently form cations. More specifically, the ones in the first column are going to form cations with a +1 charge. The ones in the second column are going to form cations with a +2 charge. Okay, and you can like unequivocally rely on that happening. If you see sodium in a compound, you can think to yourself, okay, that's Na+, because that's inevitably what it's going to be. All right, those first two columns, the elements are quite well behaved and they can be counted on to form those positive ions. So you should get used to the idea that you can predict the charge for the things, at least in those columns. All of these in the middle of the periodic table, the so-called transition metals, those are actually pretty hard to foresee the charge of because a lot of them form multiple different cations. And so we largely just sort of sidestep that as an issue for us in this particular course, to be honest. We can also make monatomic anions. That means we're going to take a neutral atom and we're somehow going to add an electron to it. Okay, the elements that are going to do this are generally nonmetals, and the most frequently seen ones are what are known as the halogens. The halogens are the elements in group 17, as our periodic table is labeled here. Okay, and fluorine, chlorine, bromine, iodine, astatine, going down the list. Tennessinium on the bottom of the list, which breaks the naming pattern, I'm afraid. And then all of those will form a -1 ion pretty much anytime you see them. So if I see fluorine in a compound, I can say I expect that to be F-, quite likely, especially if it's bound to a metal. Okay, knowing those charges says we can also write some formulas for things, right? Because we know when we make a molecule, it's going to have to be electrically neutral, and we'll talk about that in a second. One comment about this particular periodic table, you'll notice that it has hydrogen both over here in group 17 and over here in group 1. That's because hydrogen is a little bit weird. Hydrogen will form both H+ and also H- ions, okay? Hydrogen is kind of special because it starts off with just one electron. Because it forms H+, that makes it seem like it belongs over here. Because it forms H-, among other things, that makes it seem like it might belong over here. Some periodic tables, including this one, happen to put it in both places to emphasize that, okay? Over here, hydrogen is also a diatomic gas, just like fluorine and chlorine are. All those elements in the halogen column tend to form diatomics. Hydrogen does that, another good thing for putting it over there. All the elements except for hydrogen over here are metals. There is actually some, it's very difficult to do, but there is some experimental evidence that says if you get hydrogen at crazy high pressures where you can solidify it, that it does begin to conduct electricity a bit like a metal. It's just really, really hard to form solid hydrogen because the melting point is just ridiculously low, and it doesn't like to be a solid. We can also have polyatomic ions, which are groups of 2 or more atoms. Within the polyatomic clump, these are held together by chemical bonds. The overall species is electrically charged, okay, and there can be either cations or anions. I've written a few of them there. Those are probably the more common ones. Some of the most common ones we'll see. NH4 plus is ammonium, H3O plus is hydronium, NO3 minus is nitrate, SO4 2 minus is sulfate. I probably should have put OH minus on that list, which is hydroxide. Those are by far the most frequently encountered ones that we will see, okay? There's a list in the textbook that has some more of those. There's no need to memorize that. If you get at least a little bit familiar with some of them, it can save you some time and effort looking things up more frequently. But again, I'm not really a big advocate for just forcing people to memorize long lists of things or anything like that, okay? One tip-off that something might be one of these polyatomic ions is you somewhat often will see their formulas wrapped up in parentheses, okay? So sulfuric acid, for example, is H2SO4. That's a bad example. What was I thinking? Which looks like that. Let's try making something different. Gosh, let's make ammonium sulfate. How about that? That would be NH4. I need 2 of those, SO4. Right? Because each ammonium ion has a +1 charge, sulfate has a -2 charge, and so that means I would need 2 of the +1 ions in order to get my overall molecule to be neutral. So this set of parentheses there is a little bit of a reminder that that thing inside, there's a decent chance it's going to be a polyatomic ion. Okay, if I wrote, I don't know, barium nitrate, that would be Ba, which makes barium 2+. Because it's in group 2. The second column, NO3, is 1-, so I would need 2 of those to do that, right? And so just kind of get aware of those parentheses as being a little bit of a sign that you might be looking at something with polyatomic ion in it. If I form an ionic compound, we need anions and cations. Their charges have to balance. That's essentially the argument I was just making when I said we could deduce what those formulas looked like, right? If I wanted to stick to some simpler ones, I could say that sodium is in group 1, chlorine is in group 17, the halogens, so they make +1 and -1, so that would look like that, right? Magnesium is in group 2, so if I made magnesium chloride, it would have to look like this, where I would need 2 of the -1 chloride ions to offset the +2 charge of the magnesium ion, okay? Right now, the columns, the groups, those are the groups I'd like you to be familiar with and feel like you could do that, is group 1 and 2, which are the +1, +2s, the first 2 columns on the left, and group 17, which is the fluorine, chlorine, bromine, that column over there, the halogens, those are going to be -1s, okay? The forces that hold ionic compounds together are what physicists would call Coulomb forces. That's the fancy name for the fact that opposite charges attract one another, right? So once we get these ions formed, if I have a positively charged ion and a negatively charged ion and they're anywhere near each other, they're going to want to pull each other together, right? Because they're both going to be drawn to the other by relatively strong Coulomb forces. Because those forces are strong and because of how the crystal can organize itself, ionic compounds tend to form very, very nice crystals with very high melting points, right? Think about salt here, sodium chloride. You know that it's a nice crystal structure because if you, if you get coarse salt or any kind of like rock salt, like you might put in an ice cream maker or something like that, at least the old-fashioned kind, you can see the square edges on the crystals, right? The other thing about salt is you really can't imagine melting salt, right? You would not just take some salt and pour it in a pan and think you were going to set it on the stove and melt it somehow, because the melting point of the salt is just kind of ridiculously high to be able to try and do that. The reason for that has to do with the way the ions are arranged, okay? So in ionic crystal, what's going to happen is I have positive and negative ions, and they're arranged in a repetitive array, okay? This is what gives us the crystalline appearance. The easiest way to see what I mean by that is to look at some pictures, okay? I am going to, if I can find my way, attempt to trade in my pen for this pointer here because it's going to be a little bit easier to work with, okay? So there's two different models of a sodium chloride structure here. The one on the left is kind of in ball and stick form. The one on the right is more just balls pushed together. So let's suppose I picked, in this case, the gray ions are the sodiums, the green ones are the chlorides. Chlorides are indeed bigger than sodium, probably by more than they are in that picture, to be honest. But let's just say I pick out one ion, like I'm going to pick out this sodium ion right here that my red pointer dot is hovering on. Okay, you can see that right in the plane we're looking at, it's surrounded by 4 chloride ions, right? There's also going to be another one on the inside of the crystal there, and if the crystal kept going, there'd be one out in front of the screen around it as well, right? So each sodium ion is going to be surrounded by 6 chloride ions. Each chloride ion, if I had picked this green one here to look at first, I could say the same thing, right? It's got 1, 2, 3, 4 around it in this plane, one on the inside and one on the outside of there, means each chloride is surrounded by 6 sodiums, okay? So because of that, and because the forces are strong, every ion has strong attractive forces to 6 oppositely charged ions that are nearest to it, okay? The ions organize themselves into this structure because it lowers the energy of the total collection of particles, okay? Because the forces holding them together are quite strong, it's difficult to break that, that crystal apart, okay? And so that's what ionic compounds tend to look like. It's because those forces are strong that the crystal would tend to break along one of these planes. That's why the crystals that you see tend to have nice, sharp, right-angled edges to them, is because that's the natural cleaving point in this kind of structure, okay? You'll notice that you can't really pick out any one sodium and one chlorine and say these two go together, right? Because for every sodium, again, there are 6 nearest neighbor chlorines, and any one of those you could say is the one that's bound to that sodium. The thing you can say is that over across the whole crystal, we have the same number of sodiums and chlorines, right? And so it does count up like sodium chloride, even though we can't uniquely identify one sodium ion and one chlorine ion and say this is a pair that belong together, right? To do that, you'd have to get to the temperature where you could actually not just melt, but evaporate your sodium chloride to get ion pairs. That would be a very high temperature indeed before that would happen. If I take ionic compounds and put them in solution, a lot of interesting things happen, okay? That's part of why ions are interesting, is because ionic compounds generally dissolve in water. The various fluids in your body are filled with ions of different sorts, right? When dietitians talk about electrolytes and things, those are all ions, for example, that are in your body in various levels, okay? The properties of ionic compounds in solution are often very different from as solids. If you take the solid ionic compound, if I mix together 2 ionic solids, in almost all cases, nothing will happen because they're both tightly bound to each other. The ions don't really interact with the ones from the other substance. And I just would get like a mixture of two powdery or crystalline substances in most cases, right? If I first dissolve those things both in water and react the solutions, then in many cases, we will get a quick and obvious reaction. Okay, so the chemical properties of ionic compounds when they're dissolved in water can be very different from their properties when they're out as solids or as pure substances. Another thing that's interesting about ionic solutions is that they generally tend to conduct electricity, right? In a moment, I will pull up a video of a little demonstration that proves that point. It's one of the things I miss with being entirely online, is I don't get to do the little demonstration experiments in class, but we do still have some videos of them that we can use for that, right? So that fact that they conduct electricity tells us something about the solution. In order to conduct electricity, there have to be charge carriers present. All right, and in this case, those charge carriers are the ions themselves, right? The fact that the solutions will conduct electricity, which again, I'll show you in a second, implies that those solutions, unlike just neutral water, they have a substantial number of free ions in them, ions that can move from place to place across the solution. That's what's going to carry the current across my solution, is the mobility of those ions. What all of this tells us is that when ionic compounds dissolve in water to form these solutions, the compounds dissociate, right? And so here, if I take my solid sodium chloride, the solid tag here, labeling to make sure we know what that is. First of all, when I see that solid on this side and I see everything is aqueous on this side, that tells me that I had to throw the stuff in water to get this to happen, right? Because I only get my aqueous ions when they're dissolved in water. All right. So if I see this equation, I picture, okay, that's some salt, and now it's dissolved in water. Over here, these two ions are now separated from one another, so they're free to move in opposite directions. If I put an electric field across there, they're going to want to go in opposite directions because they're going to want to go, the positive ions are going to want to go towards the negative side of the electric field. The negative ions are going to want to go towards the positive side of the electric field, right? My solution overall is still neutral because I have one positive ion for every negative ion, right? So I don't have a charge on the overall solution, but I do have an increased ability to let charge move through the solution. Okay, this dissociation is really important to the reactivity of things of ionic solutions. All right, let me, as promised, I need to leave this shared screen and share a different screen for a second. Okay, I've lost track of where I am. Help. How come I can't see the mouse? Let's see, I'm there now, I think. Share screen, okay. And I want to share none of those. Let's just go for a desktop then. Let's see. All right, I believe we should now be sharing this screen, and that's the one I want. So there's a little apparatus here, which has, there's a light bulb on top. This cord is just plugged into a normal electrical socket. And down here, there's two wires that look a little bit like paper clips hanging out of the bottom of there, okay? There's a beaker down here, and what's gonna happen is some hands are gonna come in, they're gonna pour a little bit of solution into the beaker and then lower that thing down into it. If the solution conducts electricity, the light bulb will light up. So let's see what happens here. All right, so this jar says 1 molar hydrochloric acid, HCl. That is an ionic substance, and we put it on there, and sure enough, it conducts electricity, right? Because the light bulb lights up, and it's quite bright when we do that. Needless to say, if you do that with just plain water, you do not see the the light bulb light up, okay? I'm gonna skip ahead because in the video, they do a really lot of different substances, and I don't wanna take the time to play them all here. Right now, our helper is washing off the little wires, the electrodes there, and now we're gonna get another solution. This one says it's 1 molar sugar water. Okay, sugar is a carbohydrate, carbons, hydrogens, and oxygens. It is not an ionic substance, and sure enough, if you put that one on there, there is no sign of the light bulb lighting up whatsoever. Okay, and so that's the difference between an ionic compound and what we might call a covalent compound or a molecular compound. In the sugar solution, the sugar molecules don't break themselves apart to make ions. It does dissolve, but the things that are actually floating around, swimming around in the solution then are intact sugar molecules, and they don't carry a current because they're not charged. In the HCl solution, we get separated ions. We get H plus or H3O plus, a lot of people like to write that, and Cl minus, and those things can carry the charge that lets the light bulb light up, okay? Next week, probably we'll talk a little bit deeper about ionic solutions, and we'll meet some solutions in which they have a little bit of ionic character, and that means the light bulb will light up a little bit, but not a whole lot. But we'll save that for another video.